Welcome to this tutorial on theoretical insights into training instabilities in deep learning. This is based on the No IPS 2025 tutorial. When training large language model, we ideally want the training loss to go down smoothly over time. However, if you look at this curve, you will see sudden, sharp spikes during training. Why do these loss spikes happen? It turns out that the loss step size we use to train model efficiently are exactly what cause these instabilities. To understand this, let's image the learning rate or step size as a ball rolling down a valley. If we use a very small step size, the training is highly stable. The model takes small, careful steps train down to the bottom. But in the practice, we want to train much faster. If the step size is too large, the process becomes unstable, bouncing wildly back and forth across the valley works. So why do we use these large step size if they cause so much bouncing? Imagine a landscape with both sharp valleys and flat valleys. Large steps actually have the model bounce completely out back sharp areas and eventually settle into wider, faster minima. This is crucial because flat minima have driven the model from overfitting to the data. To control this bouncing, we can use a simple trick called learning rate warm-up. We start with a warm-up phase, steadily increasing the learning rate step by step before lowering it to navigate safely into that flatter region. This warm-up approach prevents early diversions and stabilities the whole training process. Welcome to background of our tutorial on optimization. We will start by reviewing classical optimization theory. Then we'll explore a model take on how large step size actually accelerate training. Finally, we will wrap up with a summary and some open problems. Let's start by reviewing the descent lemma. Classical theory tells us that if the step size is sufficiently small, the loss will decrease smoothly and monotonically. Visually, it looks like taking small, careful steps trend down a valley. But what happens if the step size is too large? The training becomes completely unstable. Instead of sliding down, the algorithm overshoots the bottom and bounces wildly side to side. We can visualize this behavior on a step size spectrum. Down at the bottom is classical theory. Here, we use tiny step size that are stable and act like smooth gradient flow. In the middle is practical deep learning. Here, we use much larger step size that are technically unstable, but still eventually converge. And at the very top, if the step size is infinite or just too large, the model delivers entirely. Interestingly, this middle unstable but conversion zone doesn't even exist for simple quadratic problem. Because of this, we need an alternative mental model. In simple linear regression, unstable conversion is mathematically impossible. The model just bounces outward. However, if we look at logistic regression, this unstable but conversion behavior is both conservable and provable. And moving at the way to modern deep learning, we constantly observe this exact unstable conversion in practice. As you can see in this diagram below, this model experiences sharp spikes in lows before finally settling down. Let's look closely at our phase transition using logistic regression. If we use a small step size, the gray line shows the loss dropping steadily, but very slowly. Now watch the green line representing a large step size. Initially, it's bound around and spike upwards. But look at the happen next. It drops much faster and overtakes the small step size. We just crosses a phase transition. The training moves from a messy, unstable phase into a smooth, unstable phase. So while large steps are initially unstable, they eventually exit that phase and greatly accelerate the overall optimization. What happens to this dynamic if we add L to regulate rotation? Imagine a valley that also acts like a basin. During the unstable phase, the model overshoots, taking massive bounds high across the variables. But eventually, it enters the stable phase. The regularization boosts the model back, helping it safely move down to the finite minimizer at the bottom. To summarize what we learned, first, training instabilities is directly caused by using a large step size. However, acceleration is also achieved exactly via this large step size. This gives us a new mental picture of optimization moving from an unstable phase into a stable phase. Looking ahead, urban problems include finding trackable measures of these trajectories and developing better step size scheduler like warm-up and decays to balance this behavior.
Optimizing to reduce the training loss to zero is only half the problem. The other half, which is also the most difficult part of machine learning, is generalization. This means how accurately your model will make predictions when it encounters new engine data. In modern deep learning models, we are facing a paradox called the over-parameterization paradox. Current neural networks have a massive number of parameters, much larger than the number of data points. This gives them an infinite memorization capacity. Experience has proven that even if you provide the neural network with a random white noise images or completely mislabel the entire dataset, the model can still memorize everything and force the training loss to exactly zero.
To clearly understand this paradox, let's look at the graph on the screen. We have a dataset distributed according to a certain trend, but mixed with noise points. According to classical machine learning theory, because our model had an excessively large number of parameters represented by a fourth-degree polynomial function, it tends to create a red curve. This curve is checked and bent extremely to try to pass exactly through every single data point. This is a disastrous overfitting phenomenon. The model has memorized even the noise. If a new data point appears, the red curve will be completely wrong because it fluctuates too widely. But the strange reality of deep learning is when you train a giant neural network using gradient descent, it definitely does not create the red curve. Instead, it automatically converges to the green curve. The green curve still passes through the data points to give a very loud error, but it maintains a smooth, simple shape and closely follows the actual trend of the data. Researchers call this phenomenon banning overfitting. The model is capable of memorizing noise, but it uses a simplest representation, thereby maintaining excellent generalization capabilities on new data. The core question of this entire video is why the neural network has more than enough power to draw the complete complex red curve. So what physical or mathematical mechanism complex red curve ultimately stop it and force it to choose a smooth green curve? Where does this implied regularization come from? When we don't add a single line of code to force the model to do so, we will find the answer by reconsidering the role of the step size. To understand why neural network can choose a smooth path, we first need a precise statistical measure of generalization. Look at this graph. The horizontal axis is the number of model parameters. The vertical axis is risk. First, we have a gray dashed line. In the real world, data always contain unavoidable noise. This noise range is called system noise, or sigma square. This is the theoretical lower power. No model can predict with an error lower than this gray line. In classical machine learning, as you increase the number of parameters, your training error pool line continuously decreases, but the test error, the red line, skyrockets. The difference between these two lines is called the generalization gap. In the classical era, models collapse because this gap expanded too much. This overfitting reached its peak at the interpolation threshold. Here, the model has enough parameters to pass exactly through 100% of the data, forcing the training error to exactly zero. But in deep learning, we cross that boundary and enter the over-parameters region. At this point, the test error drops sharply for the second time, creating the double descent phenomenon. Notice the orange arrow appearing in the right corner of the graph. It measures the distance from the model test error down to the exact system noise limit, the sigma square. This quantity is called exact risk. In modern deep learning models, the ultimate goal is not to narrow the generalization gap, since the training error is already zero. This gap always exists. Our true goal is to push the exact risk as close to zero as possible. When exact risk approaches zero, the model has reached theoretical asymptotic perfections. And what does this miracle of pushing down the exact risk come from? The answer lies in the conversion speed of the algorithm, the step size. As mentioned at the end of the previous part, the key to the model automatically selecting a simple structure lies in the learning rate or step size. To demonstrate this, let's examine one quantic curve fitting experiment. On the screen, the blue line represents the original function we want to find, while the gray circle are the actual training data points with add noise. We will use a two-layer neural network with a ReLU activation function to learn from this data. A prerequisite for this experiment is that we do not add any regularization techniques such as weight decay or dropout. The only factor affecting the result is the gradient descent algorithm. In the first run, we set the learning rate to a very small level, eta equal 0.01. When the learning rate is small, gradient descent performs extremely short updates. It gets stuck trying to reduce local error for each individual data point. As a result, the neural network creates the orange lines. This is an extremely complex function with countless linear segments checking connecting to accurately interpolate every single noise point. It fails to learn the shape of the original function at all. Second run, we keep the neural network and the data exactly the same, changing only one parameter. We increasing the learning rate to a high level, eta equal 0.5. Now the output changed completely. The neural network created the green line. Instead of twisting and turning, this function becomes incredibly simple and sparse in spots with very few key points. By ignoring the noise points, it has automatically adhered to the original function. This experiment confirms a new physical property of training process. The learning rate is not just a parameter to adjust the converged speed. It actually acts as a complexity dial for the model. The larger the learning rate, the simpler the function the model generates. So, what is the reason that last step in the algorithm are equivalent to creating a simple function? To answer this, we need to shift our perspective from the data space to the landscape of the log functions. To explain why a large learning rate creates a simple function, we need to look at the parameter space, specifically the landscape of the log function, loss landscape. The graph in front of you presents the model error level corresponding to different parameter values. There are two types of minima that result in zero error, sharp minimum and flat minimum. According to theory, sharp minima usually correspond to complex check and overfitting function. Meanwhile, flat minima correspond to simple function that generalize well. When you use a small learning rate, the gradient descent algorithm takes very short steps. If your starting point is near a sharp minimum, the algorithm will go straight down into the sharp valley and get stuck. It doesn't have enough momentum to escape. This is exactly why the model creates the check curve we saw in the previous sense. Conversely, when you use a large learning rate, the algorithm will diverge in regions with high curvature. Specifically, according to the age of stability theory, gradient descent cannot converge up the large. In fact, eigenvalue of the Hessian matrix is greater than 2 to define eta. In other words, long steps cause the algorithm to continuously pause out of sharp minima. It's forced to keep moving until it finds a region of space with sufficiently loud curvature, that is, a flat minimum, where it can converge and stop. A last learning race is precisely the mechanism that forced the algorithm to search for flatness. So, what is the mathematical significance of flatness in parameter space? We will demonstrate its power through the Lagrange matrix recovery problem, matrix sensing. Suppose we have an original matrix that needs to be recovered. We use a two-layer linear neural network. The sense of this two-layer network is a multiplication between two parameter matrices, a column matrix and a row matrix. Mathematically, each hidden neuron in the network performs an outer product between a column and a row, creating a rank 1 matrix. Since we are using an over-parameterized model, the neural network has an infinite number of hidden neurons. When all these neurons are summed together, they create a chaotic matrix filled with high-range noise, representing the overfitting of data. However, mathematical theorems show that if gradient descent converges at a flat minimum, this flatness, measured by the trace of the Hessian matrix, is equivalent to minimize the nuclear norm of the output matrix. Minimizing the nuclear norm is effectively minimizing the rank of the matrix. This mathematical drive will ultimately suppress redundant neutrons, completely eliminate the noise layer, and accurately recover the original matrix with the simplest possible structure. This is the clearest evidence that flat solutions produce simple models. Flat solutions create simple structures. This statement sounds perfect, but in machine learning, nothing is absolute. We face a paradox. Not every lab minimum is good. Look at the graph on the left. We have two minima. Both are completely flat at the bottom. If the algorithm falls into the first flat minimum, the graph on the right shows that it corresponds to a simple linear function. The model ignores noise points and possesses excellent generalization capability. This is a good flat solution. But if the algorithm falls into the second flat minimum, the story is completely different. The graph on the right shows that the model is now a complex polynomial function, spanning essentially just to pass through a single area. Why does it still create a flat minimum in the log function? Because the model is reliably confident. It interpolates the outlier with a wide range of yellow error, causing a gradient slope to completely disappear, creating a fake flat region. The conclusion here is flatness of the log function is a necessary condition, but not sufficient to ensure the model doesn't overfit. We need a stricter mathematical constraint to directly control the curvature of the prediction functions. To resolve the flat minimum paradox that produce weakly functions, we must directly measure that regardless in function space. This quantity is called total variation. Look at the red vertical bars on the screen. They represent the amount of exact curvature. The more a function twists and turns to pass through noise points, the longer and more dense these red bars become. This means the total variations is at a very high level. Do we eliminate this red bar? Yu-Xiang-Wang solution lies in this equation. The left-hand side is the total variation, the weakness of the function, while the right-hand side is lambda minus E lambda max, the sharpness of the log function in parameter space. The theorem points to a strict inequality relationship. The weakness of the function is always bound above by the sharpness of the log function. This means that when your gradient descent reaches just for the absolute minima, it is continuously forcing the right-hand side of the equation to decrease. This invisible pressure squeezes the total variation on the left-hand side. As such, jagged folds are completely eliminated, forcing the neural network to represent the smoothest possible curve. This false smoothness brings immense quantitative benefits. Let's compare the rate of error reduction with classical methods like canonic regressions. The best mathematical limit is found at big omega of n to the power of -3/4. However, when a neural network is protected by this total variation boundary, it achieves an error rate of bit O of n to the power of -4/5. In mathematics, n to the power of -4/5 approaches 0 much faster than n to the power of -3/4. Deep learning models have truly shattered traditional statistical barriers. We have reached the final stage of our journey. In the second half of the video, we realize that parameter space flatness is not enough when facing high-dimensional data space. The curse of dimensionality creates massive gap, allowing neural networks to perform narrow sorting, splitting the play to cut individual noise points. To survive and maintain generalization capability in this harsh environment, modern deep learning models utilize 3 layers of physical perception. First, using weight decay, this technique not only creates a flat minimum, but it also forces weights to low levels, thereby stripping the neuron of its ability to reach out. The decision boundary is pulled back near the data center. Second, intervening in the architecture by proactively remove the bias parameters, we ensure every boundary to the origin. The network loses its freedom for random movement, thereby giving up on twisting to isolate individual noise points. Third, changing your data geometry. Instead of letting your neural network wander blindly in dangerous voids, we use mix-up to project interpolated points to fill the space. The model is forced to build smooth bridges, connecting the data clusters together. The combination of these 3 factors, the pull of weight decay, the anchor bias-free architecture, and the breadth of mix-up had completely eliminates the neuron shifting phenomenon. And that is the big picture. The success of modern deep learning is not a black box message, nor does it only depend on a massive number of parameters. It is a subtle resonance between large steps to find path minima, strict control from regulation function, smart architectural design, and the structure of the data itself. Hope this video has given you a clear physical and mathematical perspective on the overparameterization paradox. Thank you for watching. Teacher.